I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about the introduction about the search algorithms which is used in the AI. Just some basic things we will see to it. Search algorithms in artificial intelligence are methods used to explore and navigate through a problem space to find solutions or optimal outcomes. These algorithms play a crucial role in problem solving, enabling systems to make decisions, plan actions, or uncover patterns in large data sets. They are broadly categorized into two types: uninformed. The another name of uninformed search is known as blind search, which explores possibilities without additional information. Example: breadth first search, depth first search, etc. And informed search, we are calling this informed search as heuristic search, which uses problem specific knowledge to guide the search more efficiently. Examples are A star or greedy algorithms, etc. These techniques are foundational in artificial intelligence applications like pathfinding, game playing, scheduling, and optimization tasks, etc. We'll see one by one. First, we'll move on to the introduction to search algorithms. Search algorithms plays a crucial role in artificial intelligence and computer science by helping systems navigate through problem space to finding solutions. These algorithms explore various state of a problem, looking for a sequence of actions that lead to the goal. Search algorithms are generally classified into, as I've said already, two types: uninformed. The another name of the uninformed search, we are calling it as the blind search, and informed search, we are calling it as the heuristic search. Uninformed search algorithms explore the search space without any knowledge of the goal beyond the problem definition, while informed search algorithms utilize heuristics to guide the search towards the most promising paths, improving efficiency and effectiveness. Next, we'll see the uninformed search. This we are calling it as the blind search algorithms. The uninformed or blind search algorithms explore the search space without using any additional information beyond the problem definition. These algorithms do not have any heuristics or estimates to guide their search process. They only know the initial state, the possible actions, and the goal tests. Uninformed search methods explore the search space systematically, but they can be less efficient compared to informed search algorithms. Examples of uninformed search we'll discuss in deeply. Uninformed search algorithms include breadth first search, we are calling it as BFS, depth first search, DFS, and uniform cost search. So many algorithms are there, each with its own characteristics and use cases. First, we'll see the under the uninformed search. We'll see the breadth first introduction about the breadth first search. This we are calling it as the BFS. BFS represents what? Breadth first search. This breadth first search BFS is a search algorithm that explores all nodes at the current depth level before moving on the next level. It guarantees finding the shortest path in an unweighted graph by considering all possible paths at each level before proceeding further. This PFS is a complete algorithm, meaning it will always find a complete means what? It always able to find out the solution. Complete means it always find out the solution if one exists, and it is optimal, and ensuring that shortest path is found in terms of the number of actions. However, the BFS has high space complexity because it stores all nodes at the current level depth level. making it less efficient for large spaces. The time complexity for this BFS is order of b to the power d, and both complexity and space complexity are having the same value, order of b to the power d. Next search under the uninformed search is the depth first search. This we are calling it as DFS. Depth first search, DFS, is a search algorithm that explores as far down a branch as possible before backtracking. It prioritizes depth over breadth, meaning it goes deeper into the search space before exploring other branches. While DFS can be more space efficient than BFS, DFS can be more space efficient than BFS because it only stores the current path. It is not complete. It is not a complete one. Why means in infinite, it is not complete infinite or cycle search spaces or may fail to find solution. DFS is also not optimal, all as it does not guarantee the shortest path. Its time complexity is similar to BFS, that is order of b to the power here b to the power d. BFS also the time complexity is order of b to the power d, but it may now not always find the best solution to its depth first nature, and the space complexity is also order of b to the power d. That's all about the depth first search introduction. Next, the third type is the uniform cost search. This we are shortly calling it as UCS. UCS means what? Uniform cost search. Uniform cost search is a search algorithm that expands the node with the lowest path cost, similar to BFS, but considering the cost of reaching each state. And coming to the characteristics, UCS is complete, meaning it will always find a solution if one exists, and it is optimal when the path costs are non-negative. Yes, it guarantees the optimal solution. UCS is particularly useful when the cost of actions varies, such as in route planning where distance or travel times differ. However, like BFS, breadth first search, UCS has high space complexity because it stores all nodes at a given depth level, making it less efficient for larger problem space. Okay. Next, this depth first, depth limited. The previous one is the uniform cost search. The next type is the depth limited search. This we are calling it as DLS. DLS represent depth limited search. This depth limited search DLS is a variation of depth first search DFS. Variation of DFS. Make a note of it. Variation of DFS that imposes a predefined depth limit. The algorithm stops searching when the depth limit is reached, preventing it from exploring too deeply into the search space. While DLS can be more efficient than DFS in some cases, it is not complete because it may miss the solution if the goal is deeper than the depth limit. So it is not complete, right? DLS is also not optimal, as it may find a suboptimal solution. Its time and space complexity are proportional to the depth limit. That is proportional. That is why we are calling it as this limit. B to the power L, order of B to the power L, depth limit. We are calling it as depth limit, making it a more manageable option than DFS in certain situations. So the next type in the uninformed search is the iterative deepening search. This we are calling it as IDS. Iterative deepening search combines the space efficiency of depth first search with the completeness and optimality of breadth first search. IDS performs a series of depth limited searches, gradually increasing the depth limit until the goal is found. This approach ensures that IDS is both complete and optimal when the step cost or uniform. If it is uniform, it is complete and optimal. IDES is particularly useful when the search space is large and memory is limited, as it only stores the current path. Its time complexity is similar to BFS, that is order of B to the power D, time complexity and space complex, but it is more space efficient, making it a good choice for large search spaces. So this iterative deepening search is a very good algorithm for large search spaces. The next type is the bidirectional search. The first type, uninformed. The bidirectional search is a search technique that simultaneously searches forward and backward, forward from the initial state, backward from the goal state. The two searches meet in the middle, effectively reducing the search space and improving efficiency. This approach is complete, meaning it will find a solution if one exists, and it is optimal when the stop costs are uniform. Bidirectional search has a lower time complexity compared to other search algorithms, as it effectively halves the search space. However, it requires additional space to store the states in both directions, which can be a limitation in certain cases. Order of B to the power D by 2, the same thing. We are using it. So, the second type of the search algorithm is what? Informed search. The another name of the informed search, we are calling it as the heuristic search. Informed search, we are calling it as the heuristic search algorithm. Informed search uses the additional knowledge, often called heuristic, to hide the search process more efficiently. A heuristic is a function that estimates the cost or distance to the goal state from a given state, helping to prioritize promising paths. Informed search algorithms are more efficient than uninformed ones because they focus on paths that are more likely to lead to the goal. Example of informed search algorithms include A star, greedy best first search, and iterative deepening A star, that is IDA star, which uses heuristic to reduce the search space and improve the search processes. The first we will see the introduction about a search algorithm, A star search algorithm. A star is an informed search, right? Algorithm that combines the benefit of uniform cost search (UCS) and greedy best first search. It consists of both the cost reached the current state G of n and the estimated cost to reach the goal h of n to determine the most promising node to expand. The total cost function is, we can call it as f of n is equal to, in this case, g of n, this g of n plus h of n. A star is complete. The characteristics, if you are coming into the A star, it is a complete, A star is a complete and optimal when heuristic is admissible, meaning it never overestimates the true cost. However, like UCS, the A star has high space complexity because it stores all nodes at a given depth level, making it less efficient for large spaces. So this is the first type. Next one is the, for all types, we are going to discuss the problems in detail in the next lecture. Greedy best first. Now I am giving you only the introduction. Greedy best first search. Greedy best first search is an informed search algorithm that expands the node that appears to be closest to the goal based on the heuristic function h of n. Unlike A star, it does not consider the path cost, making it less efficient in some cases. While greedy best first search can find a solution quickly, it is not guaranteed to be complete or optimal. It may fail to find a solution if the heuristic is poorly designed, and it may not find the optimal solution because it prioritizes immediate proximity to the goal rather than considering the full path cost. So the next one is the iterative deepening A star. Iterative deepening A star is the iterative deepening A star, that is IDA A star, combines the space complexity of depth first and with the optimality of A star. It performs a series of depth limited searches, gradually increasing the depth limit based on the cost function. IDA star is the complete and optimal characteristics. Complete and optimal when the heuristic is admissible. Its space complexity is low as it only stores the current path, making it more efficient in terms of memory usage compared to A star. IDA star is particularly useful when the search space is large and memory is constrained, but it may have higher time complexity due to repeated searches. So these are all the characteristics. So that's all about the informed search algorithms. Next, coming into the summary of search algorithms. In summary, search algorithms are essential for exploring problem spaces and finding solutions. Uninformed search methods such as BFS, DFS, UCS, DLS, IDS, and bidirectional search explore the search space without any additional knowledge of the goal. These methods are simple, effective, but can be inefficient for large problem spaces. That is the main drawback of this uninformed search. On the other hand, informed search methods like A star, greedy best search, and IDA star uses heuristic to guide the search process, making them more efficient and optimal when the right heuristics are used. These algorithms play a critical role in AI applications such as pathfinding, decision making, and problem solving. Hope all you have enjoyed about this lecture. Thank you. I hope everyone now has a clear understanding of search algorithms and their significance in AI. These techniques are essential for solving complex problems, from finding the shortest path in navigation system to optimizing resources in real world applications. Search algorithms are not just a theoretical concept, they are actively shaping innovations in fields like robotics, game development, and data analysis. Let's keep exploring and applying these powerful tools to create impactful solutions. Thank you.